you very much. As you said, my name is Derrold Holcomb. I've been doing this for a long time for ERDAS. In fact, I went to graduate school with the founder of ERDAS, so I've been with ERDAS since before it existed, so to speak. And I call my module, and I'm calling my presentation, Operational Radar. And that's because I'm trying to emphasize the fact that radar data is making a transition from the world of research into the world of real applications. And I'm going to talk about how I've designed the software to take things in that direction. This is my definition of what I mean when I say operational radar. I have purposely color-coded it, right? So in my mind, rapid, efficient, accurate is just one word, right? The information has to be rapid, efficient, and accurate, okay? Extraction and dissemination, I've got those together, that's one thing. It doesn't do any good if you have the answer and you don't get it to the person who needs it. So extraction and dissemination is one thing. And particularly in the world of radar, there's a lot of applications for radar data that are very time critical, okay? Simple example is location of a ship. You don't care where the ship was 8, 10, 12 hours ago. Where's the ship now? Same in flood mapping, all these sorts of things. So in the radar world, we got to get the information and get it out there. And the last color coding is information, right? We're not selling radar data. People are not going to become radar experts. They shouldn't need to, right? So what I'm trying to do here is rapid, efficient, accurate extraction and dissemination of information. That's the job here. Okay, within this context of operational radar software, I have several different categories, let's say, that I work with. The radar analyst workstation is where you work on the magnitude layer. Okay? In radar data, every pixel has two values, magnitude and phase. And the magnitude is just like optical images. It's the intensity, the albedo, what you're used to looking at. You can interpret that with your eye. And that's the radar analyst workstation. I'm going to talk about that a fair bit. The other package I'll talk about today is the interferometry wizard workflows. That's where you work on this phase layer, okay? When that radar signal comes back to the sensor, where's the wave when it hit? Top of the wave, is it the bottom of the wave, somewhere in between? Where on that long radar wave does it strike the antenna? We call that the phase. And we record that for every pixel. And you can't really look at it. You can look at it, it looks like a noisy television screen. But the interesting thing is there's more information, and certainly more precise information, in the phase than there is in the magnitude. But it's difficult to work on because you can't really look at it. So I'm going to talk about the tools we have for extracting that information. And that's things like coherence change detection, which we've touched on here, calculating DEMS, calculating subsidence. That's all done with the phase layer. Okay, the radar analyst workstation. A couple real simple things here. The human being is an amazing analyst. One simple example is you can see a road in an image and then the road kind of disappears and it comes up again over here. Anybody can say, oh yeah, there's a tunnel underneath there where that road continues. But try and make a computer program that can say this road segment and that road segment are connected together. Very difficult. But, like I say here, people are expensive, they make errors, especially when they have to look at gray images. So there's problems with the human being. We tried for many years to develop automated software. We were just going to process all this stuff and give you the answers. And what we found was you had to have a person go in and correct all the errors that this automatic software did, and you were spending just as much time editing your answer as if you'd done it manually by yourself. So what I've focused on the last 4 or 5 years is what I call this radar analyst workstation. I'm going to show you some of this stuff. But the purpose is to make it real, quick, easy, and accurate for the human being to make those critical final decisions and push that information out the door. So that's the radar analyst workstation. We'll go into it a little bit. I'll show you a lot of stuff here. I unfortunately have been doing this long enough that I've gone through all these different generations of software. Most of the stuff out there right now lives in what I call this generation 3, and you're familiar with that sort of stuff. You pick something from a menu, and you get a little GUI, you input your image, you give it an output name, you set the parameters, push the button and go get lunch, come back, read it into the viewer. Where I'm pushing right now is what I'm calling generation 4. I have an image, I want to see this, now. I don't like that, change that parameter, now. Now, one more twist. Yeah, I like that, let's try this one, okay? Real-time information extraction, that's what I'm trying to push this stuff into. And there's an example of some tests we've been doing recently on some new software. So you can see, I'm looking at a more than tenfold increase in my productivity. So we are actually getting to where we can start doing things in almost what you would call real time, or fast enough that it's functionally real time to the analyst sitting there doing it. Okay, how we approach this thing of real-time analysis into the workstation. One of the first things we put a lot of focus onto is this on-the-fly ortho correction. Right? Again, generation 3, we had to input the image, input the DEM, output name, projection, pixel size, right, all that stuff. We don't have time for that anymore. And the other thing is, in the world of radar image interpretation, people really do not like to resample pixels. Now, you know, most people when they look at a radar image, they think, wow, this is really noisy image, right? It's like a crummy spot image. The reality is that radar pixels are purer than optical pixels, right? Because with optical pixels, we always have this thing we call point spread function, right? Where atmospheric scattering causes bleed over. You can have information from 3 or 4 or 5 pixels away scattered through the atmosphere affecting your pixel, right? Point spread function we call it. We don't have that in radar. In radar, every pixel is precisely what it is. And so people working in that world do not like to resample pixels. So we have the radar workstation set up so we don't resample pixels anymore. We leave stuff in the original raw format and just analyze it on the fly. So this was the first thing we had to do, was orthocorrect this stuff on the fly. So now we don't what I call import data anymore. We ingest the data. In other words, you can't see it right here, but this is a radar sat 2 scene, I think. It's an original raw format, just as if you have it on your DVD or on your hard drive. When we ingest the data into the viewer for you to look at, we bring in the pixel values and we bring in all the associated metadata. We create the sensor model on the fly and geocode the image as we read those pixels into the viewer. Now what I'm showing here is starting in 2015 or 14, can't remember, but we set up the ability to ortho-correct on the fly. So if you have the DEM for your area, you just go here to what we call this image metadata, and you input your DEM, and then when you read into the viewer, it uses the DEM and ortho-corrects on the fly. But if you took your Inquire cursor and went down and said, what is that pixel right there? It goes back to the original data in the original raw format, the absolute minimal amount of spatial or radiometric resampling taking place. In fact, hopefully none. And here's a good example. There's geocoded, right? When you add the DEM, orthocorrect on the fly. Okay. Serious effect. Radar has serious distortions because we have this side-looking geometry. We have a ranging sensor, and you can see the huge effects. In fact, generally speaking, the rule of thumb I tell people is, however much your elevation is off in your DEM, that's how much your geoposition will be off. Okay, so if you have a 30-meter error in your DEM, that pixel is going to be 30 meters into the wrong place, right? And every pixel is going to be treated separately. So you can end up with this pixel ends up over here and this one over here, right? These images get real distorted like you're seeing here. So you have to do this sensor modeling and orthocorrection fairly precisely if you're going to work in that world of pixels. Okay, this is what I call the radar analyst workstation. This is part of Imagine. When you get it started in 2013, I think, all the radar software was redesigned into this radar analyst workstation. And the concept is, as I've said, someone is going to be working on a radar image. I want the tools that they need, and I want the data handled the way I want radar data handled, not optical data. One thing is, you have to read a radar image into the viewer before you can even activate this module, because the workstation is locked on this image. It knows that's the image it's working on. You can read other layers on top, optical data, maps, vectors, whatever you want to help your interpretation, but that always remains your base layer. And if you abstract some parameter, it goes back to this base radar image. You see a lot of the tools here. I'm going to show you a bunch of these things as we go through here. But all the tools here are set up strictly for radar. One real important tool that I'm showing right here is you see this look direction tool, right? That's because the look direction is the most important parameter in understanding radar data. And I can show you real simply. I can see that wall very clearly, and I can't see that wall at all, right? Very simple, and this wall here is some shade of gray. So it's very look direction critical to understand the image. So the software, again, is set up so that this arrow is always locked onto this image through the sensor geometry. So if I zoom in or zoom out or rotate the image, whatever I do, that arrow always retains that knowledge. So anytime the analyst is looking at something and wants to think about it, They push that button and this arrow will appear. Okay? And over the past couple of years, I've now added the incidence angle and the date because people said that's other critical information. Okay? So what I'm showing right here is this little package of what I call real-time functions. And these are enhancements that you can do very quickly into the viewer, and I'll show you some of these things. The first one is this look direction tool. And I just talked about the look direction tool, how critical it is. But this is a little example of how I show people how you use this look direction stuff. You know, once you start understanding that, to me at least, a radar image becomes more dynamic. You know, in my opinion, optical images are flat. I don't see a lot there. But here I can look at this image and I see, for example, you have a very bright line, okay? Have a really dark shadow right behind it, and then kind of a mottled gray. Well, think about that. You know, I've never been here, I don't know a thing about it, but you know, I know my radar was coming in this way, so you know, I'm thinking, okay, there's something here, bright, you know, maybe it's a wall. You know, right behind it, I have this real dark shadow, right? Because radar has these dark shadows. Right? With optical data, you have a lot of light scattered all over the room. That's not the case with radar. It's a very pointed beam. So if you're behind something, if you're in the radar shadow, it's a dark shadow. So the fact that I have such a dark shadow here makes me think, well, that's probably a wall. And I maybe could even measure the width of that shadow and estimate the height of the wall. So that's what I mean by a more dynamic scene. And I can show you other stuff if I had time. But another thing I want to point out is, you know, I can kind of see, you know, a little bit of brightness right along here. Well, is that a wall also? I don't know, right? Because based on that look direction, I really can't tell you a whole lot about something that would be oriented in this direction. That's why for visually interpreting the data, okay? Your brain is not all that good at looking at shades of gray. Your brain likes bright stuff. Your eyes love red. So we want to put the information in a color-coded sense instead of these shades of gray, which people don't really care for a whole lot. And so I want to go into this a little bit. This is an example of some of the kind of tests we do on these algorithms. Single look complex, right? That's the kind of data you want. That single look has your highest spatial resolution. Complex is that pixel with two values. Right, I want magnitude and phase. Don't throw away your phase. That's your information right there. So I'm going to be in this world of single look complex. This is a real common scenario. I have two radar images taken a month apart. Is there any change in this image? You can imagine being an analyst and being responsible for trying to find changes in gray between these two images. Very difficult, very fatiguing. So that's what these tools are directed towards. Now, I happen to find this little thing that makes a nice, cute little story. I've zoomed in, right? So now, once again, if you're going to really look at these two gray images, you're going to have to zoom in at least this close. And then you have to slowly move through that entire scene, right? Looking for subtle changes. And if you look here, you can see a little bit of stuff. I mean, once again, your eye finds this bright stuff real quick. It's good at that. But try and find some shades of gray. You don't see them so clearly. So this sequential enhancement little trick, you see now suddenly, I start seeing a linear feature over here that's kind of popping out in the data, right? You know, of course, if you go back to the original data, you'd see it. It's in the grayscale data, but you'd never find it. Now, in this particular case, this is by the Panama Canal. This is probably some sort of storage area for stuff coming down the canal. But think about this. If that was a road or a railroad track that led to a weapons storage area, chemical weapons storage, missiles, something like that, the fact that somebody is clearing a road is going to be your first indicator of an impending operation. Okay? So that could be the most critical information in this entire scene, somebody clearing that road. But you have never found it in that grayscale image. Okay? That's why people like these kind of enhancements. And I should mention, the software is set up so that as you zoom in, it automatically recalculates to the highest possible spatial resolution. So you're always, right, going back to that original data on the hard drive and processing it on the fly into the viewer at your highest spatial and radiometric resolution. Okay, Speckle. Everybody knows about Speckle, right? It's an interesting operation. Speckle is what makes radar data unattractive to people that aren't used to looking at it. It's inherent in the physics of the sensor. You can't just, fix the sensor and make it go away. So we have various algorithms to despeckle. There's one there, despeckles on the fly. I'm working on a much more sophisticated one right now, order of magnitude beyond this, but you can see where despeckling makes it easier for a human being to look at it and kind of see coherent features, or, it makes visual interpretation easier. Despeckling is not magic. It doesn't automatically get rid of all the bad stuff and make it nice and clean. When you enhance something, the other side of the scale is you are suppressing something else. Always be aware of that, okay? So despeckle is nice, unless it happens that you're looking for a mobile missile launcher that was right there and you just despeckled it away, okay? One thing I tell people to do a lot of times, if you're really doing serious work, is take your despeckled image and subtract it from your original image, okay? The difference between those two is the noise that you took out, right? If you see any structure in that noise, then you took out information, right? If it was just noise, it should be just random noise. Anyhow, despeckle is good, it's interesting, be careful with it, it's not magic. Real-time change detection. Everybody's interested in change detection. This is a cute one, I love it. These are my same two scenes, that same study area, Panama Canal. But in this case, I have both images right into the viewer. And I have another one of my little magic buttons here called Blue is New. Okay? That's a little poem. Blue is new, but red has fled. Okay, see? Blue is new, red has fled. If you speak English, you can always remember that. I haven't translated it a lot. But when I push that button, I get that. Okay? And then, it takes 2 seconds, maybe faster. Again, color-coded information. All right, zoom in a little bit. Everybody can see this ship, but you could find that ship anyhow, okay? But let's look at these two things over here, okay? A couple little red things fled and one blue thing came on the scene here, okay? Again, chemical weapon storage and a mobile missile launcher, pretty important to find those things. But go back to those original grayscale images. Would you ever have found that pixel left the scene? Okay? That's what these tools do. Contrast, inverse, and reverse. Here we're looking at one of these what we call coherence change images, CCD. We're going to talk about that a lot. Coherence change detection is the change in the phase layer. Okay? We're going to go into that a whole lot. But we're looking at it right now because we looked at some just in a previous presentation. And if you remember, bright means no change. Coherence is good. Dark means the coherence is lost, something changed. Well, that's good, except that's not the way your eye and your brain works. Your brain is used to things that are bright. It's looking for change that's bright. So unfortunately, this is exactly the wrong contrast. So it's a pretty simple little game here. You can see what I've done over there is simply inverted the contrast. Make the change be bright. That's the things your eye responds to. Your eye has more discrimination in shades of bright than it does in shades of dark. Okay? But also you can see that there's a lot of change here. Cars drove all around in here. These are all car tracks coming in here. Maybe the wind blew, it rained one day. I don't know what happened in this particular scene, but there's a lot of stuff here that I maybe don't really care about. So there's another little button you can push, and it does a nonlinear contrast inverse. Okay? I'm not interested in any kind of change. I want the significant change. And there's a couple advantages here I want to point out. One is, of course, it's a whole lot easier to see the information here. I mean, for example, you see this bright spot immediately. Was your eye drawn to that little dark spot there? Or this little dark spot out here? No, because it's not the way your eye and your brain works. So the first order of magnitude or whatever here is that this makes it easier for the analyst to do his job. Okay? Well, let's go one notch further. Remember, it's extraction and dissemination. So if you're going to go to your boss and say, sir, I need to send somebody in here, a special ops team, and find out what that is, if you show him a dark spot, he's going to go, what? It's a dark spot, you know what I'm saying? But if you show something like that, everybody responds instantly to that. Yes, bright spot. I need to go to each one of these bright spots. That's actionable information. So part of the game here is just making this information in a way that people respond to it. I always say, if you want someone to see it, make it red. Okay? Everybody will notice it. And it sounds trivial, but it's actually fairly important, right? Because what's the job here? The job is giving people information. Make it easy for people to understand and perceive the information. That's all we're trying to do here. Okay. Those are kind of what I call these real-time functions right into the viewer. There's some other tools I want to show you here. These are what I call the display modes, right? And like I said, we're working in the radar analyst workstation. We're working on the magnitude layer, the intensity, the albedo, whatever you want to call it, okay? And so we generally, when we read the image in, we're looking at the magnitude. Even if I read an SLC image in, I project the magnitude. But I have a couple of what I call different modes. And we're going to take a look at them. First, we're going to look at what I call the edge enhance mode. And what I do here is, okay, this is a radar image, C-band. This is very interesting. This is a C-band of a geosyncline in the Amazon basin. So we are not penetrating the canopy here. This is dense, dense vegetation. We're seeing the subsurface structure and topography probably reflected in the top of the canopy. Okay, hard to believe, but for one, it's there, and for two, I used to do some archaeological work, and I was working with guys down in Mexico, Guatemala, and some of the old archaeologists told me that, you know, back in the old days, they flew around with little airplanes and looked for trees that were sticking above all the other trees. Because if there's a tree sticking up, there'd be like a pyramid underneath it. Very strange phenomenon. But anyhow, you see a geosyncline there. But what I do is I push this button, which I call edge enhance, and I basically take my radar image and pretend it's a DEM. Okay? And then I take that radar image DEM and make an artificial shaded relief. And then I have a real-time tool up here where I can move the illumination around. All right? Kind of to enhance linear features. Radar is really rich in linear features. Right? What I'm playing with here, if you remember, I talked about I can see this wall real clear, right? And I can't see this wall at all. Well, every wall in between is some shade of gray, right? Well, the ones that are really kind of weak and not easy to see, by playing with this little tool, I can pull them out of the data a little bit, right? So I can play with my real-time tool and enhance different lineaments here. And then the software is set up so I can draw an annotation layer on top of it. So if my job was to do a structural mapping in this area, I could go through and create that by using this real-time tool. I use it a lot of times also when people are monitoring human activity, because people like to make straight lines, edges, those kinds of things. You can pull out the fine structure of like an airport or things that have that linear character to them. So that's the edge enhance mode.